Welcome back, everybody. Hope that water break was refreshing. So we'll now work through two practice problems using the multi-period binomial formulas that we just learned. We'll start with this problem right here. It's going to be actually a two-period binomial problem. We could solve it using our two-period methods. But instead, what we're going to do is we're going to apply the formulas we just learned to get some good practice. So the problem statement is going to be as follows. We're again interested in Microsoft stock. Microsoft does not pay dividends, and it's currently priced at $100 per share. There's going to be two dates in the model, 0 and 2. Time 2 is in years, and this is equal to capital T, 2 equal to capital T. The model is going to have periods that span a year, so each year the stock is going to move either up or down. There's 2 years, so the number of periods in this model is going to be 2. The assumptions behind the problem are as follows. In each year, the stock price can either move up or down. If the stock price moves up, the gross rate of return is 2. If the stock price moves down, the gross rate of return is 1/2. The stock halves itself. It can move up or down each period, so there could be a total of either 2 up moves, 1 up move, or 0 up moves if it moves down twice. Okay. Continuously compounded risk-free interest rate is 0%. Assume there's no arbitrage. And what we want to do is instead of pricing a European call like we did last time, we want to price a European put option on Microsoft with a strike of K equal to 100 and a maturity of 2 years. Okay. So to do this, we start by just writing down all our inputs, and then we just start plugging things into our formulas. So we have a total of T equal to 2 years and N equal to 2 periods. Okay. Each period is going to correspond to a length of 1 year. In each period, the economy can either move up or down. Okay, so the economy can either move up or down in period 1, and again up or down in period 2. So the number of possible up moves that there are in the economy, up moves, is the economy can either move up 0 times, in which it moves down twice, moves up once, and then down once, in which there's 1 up movement, or it can move up twice. Okay. Other inputs, the stock price is currently priced at $100 today. Risk-free interest rate is 0%. Okay. Gross rate of return, conditional on an up movement, is 2. Gross rate of return conditional on a down movement is 1/2. We're assuming there's no arbitrage, and we want to price a European put option with a strike of K equal to 100. Okay. So to price this put option, what do we need to do? We need to use the FTAP and calculate the discounted expected payoff to the put option. To do this, we need to know the payoffs of the put. We need to know the risk-neutral probabilities. And so the put payoffs are also a function of the stock's price at that date, so we'll start there. We know that the stock's price at date capital T is a function of the number of up movements. It's equal to the U to the I, where I is the number of up movements, D to the N minus I times S0. There's 3 possible I's that could occur. The stock could either move up twice, move up once, or move up 0 times. So what we need to do is we need to calculate ST under these 3 different scenarios. Calculate the stock price if it moves up twice, up once, or 0 times to begin our computations. If the stock price moves up twice, then what happens is that this formula will be equal to U squared times S0. U is equal to 2. Squared is the number of I movements up, times 1/2 to the 2 minus 2th power, that's the 0th power, times S0, which is 100. This is just equal to 2 squared times 100, which is equal to 400. ST of 1 up movement is going to be given by U to the 1th power times D 1/2 to the N minus I-th power, or 2 minus 1 times 100. This is equal to 2 times 1/2 times 100, which is just equal to 100. And the stock price, if there are 0 up movements, is equal to 2 to the 0th power times 1/2 2 minus 0 times 100. It's equal to 2 to the, it's equal to 1 times 1/2 squared times 100 equal to 25. This is the same exact setting we worked with when we had the two-period binomial model. And notice that the payoffs of the option are exactly the same when we use this formula as when we use the two-period binomial setting where we explicitly calculate the states. The only difference now, okay, so this ST of 0 corresponds to the DD state. ST of 2 corresponds to the UU state that we had. But now the only difference is we just have a singleton right here that summarizes the payoff in both the UD and the DU state. The trick behind this multi-period binomial setting is that the risk-neutral probability formula will then attach more weight to this to reflect that it's actually encompassing 2 states, while the other payoffs are only encompassing 1 state. The second part of the problem, what we need to do, we have the stock prices at this terminal date. And so the next logical step that we need to do in order to calculate out the price of this put option is to calculate the put payoffs in each of these scenarios where the stock price moves up or down. The put option payoff depends on the number of up or down movements. Okay, there's either going to be 2 movements, 1 movement up, or 0 movements up. The payoff in each of these states is always going to be given by the max of K minus the ST value, ST of 2 in the first scenario, K minus ST of 1 in the second scenario, and K minus ST of 0 in the third scenario. Plug in inputs. Put price, or the put payoff, if there's 2 up movements, is equal to the max of K, 100, minus the stock price, if there's 2 up movements, 400 and 0. This is equal to 0. Put payoff, if there's 1 up movement, is equal to the max of 100 minus the payoff on the stock if there's 1 up movement, which is 100 and 0, which is again just 0. And there's going to be a positive payoff when there are 0 up movements because this means there are 2 down movements, 100 minus 25 and 0, which is equal to 75. Okay, so we have the put option payoffs given this formula. The only thing we need to know now to compute the put price is the weights that we attach to them, or the risk-neutral probabilities. Here again, we just use the formulas that were given. We need to find the risk-neutral probability of 2 up movements, 1 up movement, and 0 up movements, and apply these weights to the payoffs. First step for computing risk-neutral probabilities is you calculate the probability of a single up movement in any given state, always equal to e to the r times t over n minus d over u minus d. Plugging in these inputs, e to the 0.00 times 1 minus 1/2 over 2 minus 1/2. Same as when we worked with the two-period model. It's equal to 1/3, and 1 minus qu equal to qd, or qd equal to 1 minus qu is then equal to 2/3. Okay. Calculate the risk-neutral probabilities. We want to calculate the risk-neutral probability of the stock moving up twice, up once, or up 0 times. We denote these probabilities as Q sub I, and we want to compute Q sub 2, Q sub 1, and Q sub 0. Okay. To do this, we just apply the formula. Q sub I equals to n choose I, Qu to the I, 1 minus Qu to the n minus I. Q of 2 is equal to n, 2, choose I, 2, times Qu, which is 1/3, to the ith power squared over 2 times 2/3 to the 2 minus 2 power squared, 2 minus 2th power. 2 choose 2 is equal to 2 factorial over 2 factorial over 0 factorial times 1/3 squared. This is going to be equal to 1. Work out the math. You'll see this is equal to 1/9, which is the exact same thing as QUU probability in the prior problem. Okay. Q of 1 then is given as follows. It's n choose I. N is 2. I is 1, times 1/3 to the ith power, which is 1, 2/3 to the n minus ith power, which is 2 minus I. 2 choose 1 is equal to 2 factorial over 1 factorial over 1 factorial, times 1/3 to the 1, 2/3 to the 1. This is equal to 2 times 2 over 9ths, which is equal to 4 9ths. Okay, note this. The 2 9ths was equal to either QUD or QDU in the previous problem. Okay, what we talked about here is that this ST of 1 summarizes the possibility, the payoff in two possible states. And so what we're seeing is that the risk-neutral probability attaches double the weight to this state or this event because it's taking into account that it's 2 times the probability of one particular state. Finally, the risk-neutral probability of 0 up movements is given by 2 choose 0, 1/3 to the 0, 2/3 to the 2 minus 0. This is 2 factorial over 0 factorial 2 factorial times 2/3 squared, which is equal to 4 9ths as well. Note that we're on the right track. Notice the risk-neutral probabilities, they all sum up to 1. That should always be your guess and check right there. We now have all the inputs we need to price the put option. Okay, all we have to do is plug them into the FTAP. FTAP says that the price of the put option is equal to the risk-neutral discounted expected payoff. This, in this particular form, is equal to e to the negative RT times the sum from I equals 0 up movements to 2 up movements, probability of I up movements times the put payoff with I up movements. This is equal to, you break it out, e to the negative R times t, Q of 1 times PT of 1, Q of 0 times PT of 0, start subbing in the i's, plus Q of 1 times PT of 1, plus Q of 2 times PT of 2. Plug in the numbers now, e to the negative 0.00 times 2. Q of 0 is 4 9ths. Put payoff in this state is 75. Plus Q of 1, 4 9ths, times put payoff in this state 0, plus Q of 2, which is 1 9th, times 0. What you'll see is that this works out to 33 1/3. So the put option price in this model is going to be 33 1/3. It's exactly equal to the call price from the last setting, which makes sense because there's risk-free rate of 0 and it's an at the money option, so we know it's correct. You could equivalently solve this problem using the same methods that we did in the prior lecture. Okay, so if we flip back into our prior problems where we had the big tree and we solved everything out, you could do this equivalently. It actually probably take you less time to do it with the tree in this case, but as we'll see in later models, as you increase the number of periods, this way is going to be much, much quicker. Okay, so we're going to work out one more problem. It's going to be a little more complex. Okay, it's going to have 4 periods, and we're going to work through it. This one will be actually much more complicated than usual. We won't ever deal with something like this in a exam. Okay, so it's understandable if you want to allocate time away from really understanding this problem, but we'll see how we can use it in 1 second. Okay, so I'll read the problem statement. We have Tesla stock. Tesla stock is priced today at $500 per share, and Tesla does not pay dividends. We're going to have 2 dates, 0 and 1. 1 is equal to time capital T. And what we're now going to have is length of time equal to quarters. So we're going to have n equal 4 periods between here. In each quarter, the stock price, as usual, can either go up or down. Okay? If the stock price goes up, the gross rate of return is 1.25. If the stock price goes down, the gross rate of return is D equal to 1 over 1.25, which is 0.8. Risk-free rate, 0%. We want to price a European call on Tesla that's at the money, strike of 500, maturity of 1 year. What is the price of this call option? We'll use the same formulas as we did before to calculate this out. We might actually need a little more paper. Okay, we did before. Okay, so we'll start by writing down our inputs. Capital T is 1 year away, and we have N equal to 4 quarters. Okay. In each period, the market can either move up or down, and the stock can either move up or down. There's 4 states. Okay, so the stock price can either move up 4 times, it can either move up 3 times, it can either move up 2 times, 1 time, or 0 times. So the number of up moves in this model is I equal to 0, 1, 2, 3, or 4. If you were to do this in terms of the actual tree and drawing it out, it would be very messy, very quick. I think you'd have 2 to the 4th or 16 different states you'd have to deal with. And here we're actually going to see we're only going to need to compute things related to 5 different types of up movements, linearly increasing computation time instead of exponentially increasing. Okay. Stock price today is $500. Continuously compound risk-free rate is 0%, and we have a strike of $500 on a call option on Tesla. To price the call, again, we need 2 inputs. First, we're going to need the payoffs of the call option. Second, we're going to need the risk-neutral probabilities. Payoffs and risk-neutral probabilities both depend on I, or the number of up movements. And in addition, the call option's payoffs depend on the price of the stock with each number of up movements I. Okay, so we'll start by calculating out the stock price in each of these scenarios. ST of I equal to U to the I, D to the N minus I times S0. Okay, so there are 5 different possible I's here. There's 4 up movements in a row, 3 up movements total, 2 up movements total, 1 up movement total, or 0 up movement total. The stock price, if there's 4 up movements in a row, is going to be given by U, which is 1.25, to the ith power, which is 4, times D, which is 0.8, to the 4 minus 4th power times 500. If the stock price moves up 3 times, the payoff, or the price, is going to be 1.25 to the ith power, 3, times 0.8 to the 4 minus 1, or 4 minus 3, excuse me, times 500. If the stock price moves up twice, it's equal to 1.25 squared, times 0.8 to the 4 minus 2, times 500, just plugging things into the formula. If it moves up once, it's 1.25 to the 1, times 0.8, 4 minus 1, times 500. And if it moves up 0 times, it's 1.25 to the 0th power, times 0.8 to the 4 minus 0, times 500. This first one is equal to 1.25 to the 4th times 500. This is going to be equal to 1,220 and some change. In the second one, it's going to be 1.25 to the 3rd, 0.8 to the 1 times 500. This is going to be equal to 781.25. In the occurrence where there's 2 up movements, it's going to be equal to 1.25 squared times 0.8 squared times 500. This is just going to be equal to 500. Those 2 will cancel each other out. 1 up movement, it'll be 1.25 to the 1, 0.8 cubed times 500 equals to 320. And if there's 4 down movements, 0.8 to the 4th times 500, stock payoff price is 204.80. Okay, so we know the stock's price. The put options price is given by put options payoff in state I. It's given by the max of K minus ST of I and 0. So we can calculate the put options payoffs for each of these number of movements. PT of 4 is equal to max K, which is 500, minus ST of 4, which is 122. Whoops, we're calculating a call option. Excuse me, I'm sorry. Okay, could have worked through the put, no, just different computations. Okay, call options payoff, okay, equal to max ST of I minus K and 0 for I up movements. Call options payoff, if there's 4 up movements, is max 1220.70 minus strike of 500 and 0. This is just equal to 720.70. Call options payoff, if there's 3 up movements, is max of 781.25 minus 500 and 0. This is 281.25. And for all the remaining values, CT of 2, CT of 1, CT of 0, okay, note that the stock price is at or below the strike, so the call will not be exercised, so the payoff to the call is 0 in all of these states. Okay. We now have the call option payoffs. We just want to calculate the risk-neutral probabilities. The risk-neutral probability of a single up move in any given quarter is equal to E to the R times T over N minus D over U minus D. Inputs, 0.00 is the risk-free rate, 1/4 is the length of time, minus D, which is 0.8, over U minus D, 1.25 minus 0.8. You're going to see that this is equal to 4/9. Okay. Then what we want to do is calculate the risk-neutral probabilities attached with each of the I up movements. We have Q of I in general is N choose I, QU to the I, 1 minus QU to the N minus I. Now I'm going to allow you to compute most of these on your own. Okay, I'm just going to give you the solutions. Q of 4 is going to be equal to 4 factorial over 0 factorial times 4 factorial, 4/9 to the 4th power, which is going to be equal to 0.095. Q of 3 is going to be equal to 4 factorial over, these two should be reversed right here, excuse me, 3 factorial times 1 factorial, 4/9 cubed, times 5/9. Okay, QD is equal to 5/9, which is going to be equal to 0.305. Q of 2 is going to be equal to 4 factorial over 2 factorial, 2 factorial, 4/9 squared, 5/9 squared. It's going to be equal to 0.366. Q of 1, Q of 2, Q of 1, Q of 0 aren't going to matter because call option payoff is 0 in those states anyways, but we'll compute them to begin with. Oh, I'm sorry, these are a little bit backwards. My computations are wrong. Okay. This, for the up movement right here, it's 0.039, 0.195, and 0.366. Sorry about that. Okay, Q of 1 is equal to 4 factorial over 1 factorial over 3 factorial, 4/9 to the 1, 5/9 cubed. This is going to be equal to 0.305. Q of 0 equal to 4 factorial over 0, 4, 4/9 to the 0, 5/9 to the 4th. It's going to be equal to 0.095. You can sum these up, Q of 0 plus Q of 1. You can confirm this, plus Q of 3 plus Q of 4 is going to be equal to 1, consistent with the probability measure. Final step is just to weight the option payoffs by each of these probabilities. Call options price is equal to the risk-neutral expected payoff, discounted back, e to the negative RT, I equals 0 to n, which is 4, Q of I times CT of I. This is equal to e to the negative r times t times Q of 0 times CT of 0 plus Q of 1 times CT of 1 plus all the way out to Q of 4 times CT of 4. Start plugging in inputs. E to the negative 0.00 times 1. Q of 0 is 0.095. Payoff is 0. Q of 1 is 0.305. Payoff is 0. Q of 2 is 0.366 times 0. Q of 3 is 0.195. Payoff in this state is going to be equal, or this number of up movements is 281.25. Q of 4 is 0.039, but has a large payoff, and it's going to be 720.70. Work all this out. What are you going to see? Check my math. Call price is going to be somewhere around $82.95. Okay, so that's a lot. We'll never do anything this complicated on a test because obviously it takes forever. But in general, what you can do is you can use this. You can program it up in Excel, Python, R, whatever you want, Julia, and you can use this to price options in the repeated tree within arbitrary number of periods. So that wraps up the second part of lecture 13. Take a quick break. We deserve it. We'll resume the lecture in the next video.